Okay, guys, to continue our discussion on fasteners. So, in our previous lecture, what we have derived is actually the equation for the bearing strength of the bolt. Okay, which is the basis of the LRF equations we will be using in the problem. So remember that our area here considered is simply the projected area. Okay, so we have here a projection of the bearing area, okay, by uh, the bolt diameter to the plate, okay, or the member thickness. Okay, so if we have here the bolt diameter D, so we simply make a projection of the diameter, okay, and the thickness to get the bearing area. So this is now your bearing area. So the LRFD considerations on this is primarily based on this derived equation, which is perhaps a very conservative formula, no, in that regard, since we have to take note that bearing stress is the failure on such a bearing strength is uh, not that critical compared to shear, bolt shear, and the plate limit state failures that we have discussed in our tension member design. Okay, so I'd like to you to understand these cases in order for us to be not to be confused on the usual conditions, wherein, as I have told you, the edge distance LE is simply 1.5 times the bolt diameter, and the center to center distance is 3D. Okay, so this is the rule of thumb that I'm referring to in my first lecture, that whenever we see the edge of a plate or a connection and you have a bolt there, LE simply refers to the center distance of the bolt from that center to the edge. Okay, and of course the spacing S is defined as the center to center distance from one bolt hole to the other. And the rule of thumb is such that this is simply equivalent to at least 1.5 times the bolt diameter, and this is simply equal to 3 times the bolt diameter. So in such a scenario, uh, we start maybe from uh, the less critical case. So this is the less critical case, since you allow movement by the ovalization of your hole, no, exceeding a very uh, shall I say considerable amount of distance. This is actually 1/4 of an inch is big, And allowing movement simply states that your connection is non-slip critical. Because if your connection is slip critical, then you cannot allow movement because of the existence of friction. And if we start here, we can say that your L, if I substitute the value of L uh, in terms, okay, let's say LC in terms of a factor, let's say K times D, then K is simply equal to, sorry, your D is simply equal to to a value of LC and all over K, where LC is again only the edge distance, LE minus 1/2 of the diameter of the bolt. So this is the relationship between LC and LE. Okay, so if I now consider my K value here to be uh, a 2, okay, so my K is equal to 2, then my LC here is simply equal to uh, sorry, not I do not refer to the value of K, but rather to the value of LC here, okay? So if my LC here is simply equivalent to 2.5, or sorry, 2 times the diameter D, and I substitute T in terms of LC over K, I can now compute for the K value. No? So the K value is simply equal to 3.1. Okay, so K is simply LC. What's my LC? So this is 2 times the diameter divided by the diameter. So this becomes now 2.0. Okay, so my K value here is 2.0. And if I substitute D here on the basis of this equation, so I simply put an LC there, and 3.1 will be divided by my K value of 2, I will get a 1.5 here. Okay, so this 1.5 was obtained from the value of 3.1 divided by 2.0 is approximately 1.5. Okay, so what I'm trying to tell you, class, is that if my LC is 2D, then my LE is slightly bigger than 2D, in which in the rule of thumb is more conservative because this is only 1.5D. This is greater than this one here. Okay, so what will happen now is if K is has a value of 2 here, then my K here will simply be equal to, using the same result, will simply be equal to 2.5. And my K here will simply be equal to 3, and my K here will simply be equal to 4. Noting that always your LC is simply equal to the K value multiplied by D. Okay, LC is 3D, and LC here is 4D, which are actually conservative values, very much greater than LE. Okay, the only difference is only this half diameter decrease on LE in as much as LC is concerned. So the formula here, as based on this LRFD equation, I say is very much conservative. So for the minimum spacing of the bolts in line of the transmitted force, we can now define the formula upon which the above equation was derived again. So Rn is simply equal to Fu T times Le. Okay? So this is again a projection And if I consider now my criteria for safety, which is PU is equal to VRN, this is now related to your capacity versus the loads Q, okay? So versus the loads, in this case it's PU, okay? So capacity uh, Rn or Pn versus the load Pu. So this is now Pu is equal to Vrn, therefore Rn is simply equal to Pu over phi. Okay, so substituting this value here, Pu over phi divided by FUT. So this is now Rn, Le. Okay, so taking note that in our figure here, Le is simply equivalent to this edge distance is symmetrically equivalent to this edge distance, wherein adding it up, okay, for the spacing, adding d over 2 to get your spacing requirement. So S is simply uh, uh, this value here plus d over 2. This is now my center to center spacing for my uh, uh, two consecutive hole here. So this is my formula for S. If I want to get S, this is just the formula to use, no, on this basis. And then take note that again, for the rule of thumb, the minimum bolt spacing and the minimum edge distance must always be greater or equal to 3D and greater or equal to 2D. This is slightly increased because of this situation we're in. This is now my minimum uh, value for K used in my LRFD equation. So this was slightly increased. The rule of thumb was slightly increased by from 1.5 to 2.0. Okay, so that is for your uh, LE requirement. Now for the maximum edge distances, these are based on uh, on uh, on some study on the maximum distance upon which your bolt will actually hold the connections together as a unit. Okay, so if the edge distance and the center to center spacing are very big, then the connections might end up into acting individually or separately in resisting the forces. Okay, so this is just a precaution on not over estimating the values of LE and S because of the bearing failure consideration. So for the minimum edge distances, as based on the table now, for sheared edges, it has nothing to do with this derivation, because this is only true for bearing consideration. So if the problem is about shear failure, then we can go into the minimum values of LE and apply. Maybe we can also apply this AISC guideline to give us a rule of thumb for the edge distances and the center to center spacing. So you just refer here uh, on this refer uh, the shear consideration using this table. So we also have here a summary of the design strength of an A325 and 490, considering a thread exclusion and a thread inclusion on your bolt area. Okay, so when threads are not included from the shear planes, etc. So these are the tension strength, shear strength that are that will be used, no, in our computation for the mode of failure, the failure limit state on bolt connections. So let's have an example problem, a simple problem to demonstrate the above formula. So we consider tension member bearing type connection as shown. So we have to determine the tensile capacity of the connection for X bolt. When you say X bolt, the threads are excluded, no? And N bolts in which the threads are included. In this example, we use AISC approach, assuming that the service live load is 3 times the service dead load. So material specifications are ASTM 8325 bolts and ASTM A572 with a grade 50 steel plate. Okay, so this is simply a steel plate with this connection. Length of connection is 6 inches in total. FY, FU, and FUB are given. No? So we assume standard size hole. Plates are 5/8 by 6, so the thickness is 5/8. Okay, so standard size holes meaning to say that okay, so what is the hole, the bolt diameter? 8325 bolts, capacity 3 times, there are no given, huh? Okay, so the nature of this note here is on the use of the cases, no? Upon which hole ovalizations are considered or not considered. And of course, the bolt must be given. I think the bolt is a 7/8 inch. Okay, so it was not included in the problem. I missed on it. So the diameter of the bolt here, dB, is simply equal to 7/8 inches. Okay, so the area gross is simply the area of the plate. Okay, 6 times 5/8. And then the net area is simply equivalent to 6 times the reduction. No staggering was included. So we have 2 holes, and the equivalent diameter is 1/8 larger than the diameter of the bolt. So this is 1 inch. Okay, times the thickness. So the effective area is simply the shear lag coefficient U is equal to 1, because we have all elements connected. We only have plates. So this is 2.5. Okay. So AN is 2.5. Therefore, your A effective is 2.5. T is equal to 5/8. Phi is equal to 0.75 inch. So consideration of limit state, we don't check on block shear failure mode. So we have, for the yielding at the cross section, we have this in, I think this will be in kips, no? And for the fracture, the connection, we have this. So this actually governs as far as these two are concerned, okay, for your capacity. So consider the design strength per bolt. So we are now through with the member design or the member analysis. Okay, so we go now to the connection itself, which is of course the bolt. Okay, so we are now referring to the connectors or fasteners as far as this is concerned. So the area of the bolt is pi over 4, 7/8 inch squared, 0.601. We have only one plane in shingle shear. So phi RN is simply your phi, 0.75. So that's phi. And then this is your RN. Okay, RN is 0.5 FUB MAB. So this is considering no reduction on the thread. Okay, so if you go back to the shear formulas, we have this is 0.5 FUB MAB, where AB is simply this one, and M is 1, and FUB is simply the bolt rupture strength, ultimate strength, equivalent to 120 KSI. Okay, so we have VRN equals 27.059, but this is only for one bolt. Okay, so this is good for one bolt only. Okay, so consider the design bearing strength for each bolt. So LC is simply your what's this 1.5? This is the center to center spacing of the bolt as given here. Sorry, center to edge spacing of the bolt. So this is L. Actually, this is your LE. Okay, not yes, LE. So this is LE minus 1/2 of the diameter of your bolt, which is 1.031 inch. Okay, so we now use this formula because this is the common, okay, this is the common case, okay, which is the case 1 scenario I was referring to in the lecture here on top. Okay, so we are referring it here. Okay, so this is the capacity. Okay, for the shear formula, I'd like to go back here on the shear formula of 0.5. This is tensile, this is shear. Okay, so this 0.62, and then this is a multiple point. Okay, so this is the one that I'm talking about earlier, wherein there's no reduction in the bolt because the threads are not included in the area. The strength of the bolt in terms of its effective area. Okay, so okay, let's go back now to the shearing strength computation. So if I compute this, I use phi as 0.75 for bearing, so I get 37.07 sorry, 37.705 compared to this. Okay, so I compare shear versus bearing. So this is the bearing strength. This is the shear strength. So compare the two, the lower value will prevail, and this is now our shear strength. But this only for one bolt. We multiplied by 4 fasteners, we get 108.24. And comparing now the connection, we now compare the connection and the plate capacity. Okay, so if we look into the plate capacity here, it's 168 and 121. So your connector strength is lower, so this will now govern. No? So connection is more critical. No? So that will govern. Okay, so compare with the plate strength of 121.875 keeps the fastener strength governs, hence the strength of the connection is now 108.24. And relating to the design strength with service load levels, we taking note that we have the dead and the live loads are basis for your factored combination here. Okay, so we now simply equate this with this. We know that the live load is 3 times the dead load, so we just plug it there, and then we compute for the dead load. So the dead load is 18.04, the live load is 3 times 18, so this is now the live load. Therefore, the total service load is simply the unfactored loadings coming from the dead and the live. We simply add here, so this is now your total service loads. Okay, so this is 70.16 considering thread excluded. No, so we refer to the 8325X bolt. So threads are not included or threads excluded. So when you say excluded, if I have here a bolt, I see to it that the threads here will not be a part of or will not be affected by the shear plane. Okay, so this is now the shear plane. Of course, if the threads are included, we use the same procedure, but we can simply use a proportioning a procedure. We simply get your VRN for the 8325 end bolt. Okay, so take note that the only difference is this point 4 here. This is a reduction due to thread, due to the presence of the thread, because they are included, no? So this is point 0.4. You get 21.648. You just divide it from the capacity a while ago, which is 27.06. You get a percentage of 80%. Applying it to the dead load computed on the basis of the thread excluded, we now get quickly your value for your total working load, which is of course less than, okay, the value for that in which your A3 to 5 bolt threads are excluded. Okay, so that's it for a very basic a demonstration of how to use or design a connection considering shear and bearing failure as implied on this particular problem. Thank you very much for listening, and I'll see you on the next video.